Hello everyone, my name is Jonathan Delagostin. I'm from Federal University of Santa Maria and I'm here to present a paper which title is Predicting the Movement and Tension and Controlling the Grip of Myoelectrical Active Prosthetic Arm. In a previous work, we proposed a complete and modular design for developing a prosthetic arm. This paper intends to implement the following parts of the design: predicting the hand movement using surface electromyography, SEMG, and controlling the grip of the prosthetic arm. First, we need to define a subset of possible hand movements. These movements should be predicted by a machine learning model, using SEMG as input and replicated by the prosthesis. They were selected based mainly on the frequency of use in the daily tasks and the possibility of practical implementation by the prosthesis. They were five movements: tripod, medium wrap, lateral, power sphere, and rest, as we can see in this picture. The 3D model of the hand was designed to reproduce at least the five movements cited earlier. Each finger has one degree of freedom, with the exception of the thumb, which has two. The transmission is performed by a system of articulated bars. This allows for better control and greater precision in opening and closing the fingers. We used polylactic acid (PLA) for printing all the parts. The electrical system is composed of six servomotors, six current sensors coupled to each servo, one SEMG sensor, one analog-to-digital converter, and a Raspberry Pi 3 Model B that controls all the other parts. The SEMG signals were acquired in the following steps. First, three disposable electrodes were attached to the forearm of one of the project's researchers. Two electrodes were placed longitudinally on the surface of the long palmar muscle to capture the signal, and the other near the elbow in a region of low muscle activity, serving as a reference point for the readings, with the sensor coupled to the two longitudinal electrodes, as we can see in the figure. Subsequently, four SEMG acquisition sessions were carried out. Every trial consisted of 60 repetitions of each of the four movements, as we can see in the figure, each repetition being interspersed with approximately 2 seconds in the resting position. Then, the SEMG data acquired was labeled. The points corresponding to the beginning and end of each repetition were defined by visual expression, based on the sudden change of signal, since the rest interval is easily discernible from the others, as it presents relatively less intense and less variable signals. All the other points between the intervals were then filled with the corresponding label via script. We can see the classes are unbalanced, since the rest position was present in all the acquisition sessions. The data was then segmented into sliding windows, with an increment of 0.01 second. The windows lengths used were 0.2 and 0.4 second, each one corresponding to a different training session. The data was partitioned into three sets: 20% of the samples for the testing set, and the remaining 80% were divided between the training (90%) and validation sets (10%). We used as our model a combination of convolutional neural networks layers for automatically extracting the features from the input data, and LSTM layers for capturing the temporal characteristics, along with dropout and batch normalization layers for reducing the overfitting, and finally a softmax layer that outputs each class probability. Considering the movements we choose, it was observed that defining the exact position of the fingers for each of them was not possible, since the precise geometry of each object to grab is not known beforehand. A possible solution to this problem is to initially perform each movement, grabbing a particular corresponding object, and store the positions of each finger. Then, when performing the same movements but with objects of different dimensions, those stored positions will be used as an initial position reference, and then must be corrected and updated to correctly hold the new objects. Thus, for the processes to be able to correctly pick up and release an object, it was necessary to implement some sort of control algorithm. We implemented a strategy depicted on the figure. The plant receives a position command to the servomotor and outputs a current measurement of the servomotor. The current is converted to a proximity value in the range of 0 to 1, where 0 corresponds to no contact of the processes with the object at all, and 1 corresponds to the maximum contact, where the servomotor cannot move anymore at the stalled current. This conversion is performed by a polynomial function, estimated from assays where we attached a FSR, force sensing resistor, to the tip of one finger and collided it with an object. This value is then compared to a reference of proximity, R of t, generating an error, E of t, that is fed to the controller. In order to test the control algorithms for the prosthesis without the need for physical activation of the servo motors, we came up with the idea of implementing a simulator. This simulator also prevents unnecessary wear of the parts that make up the prosthesis, especially in the initial testing phase, when a poorly calibrated algorithm can eventually cause irreversible damage to the set. This simulator is very simple, serving just as a black box, where there is an input position command to the servomotor and an output measurement of current in the servomotor. Tests of collision of one of the process fingers with objects were then carried out, with the servomotor current being stored. These tests were used to capture the current dynamics when the rotor is in contact with an object, as well as to estimate the proximity between them. They made possible to obtain general curves of current versus proximity, enabling the simulation of current values as the rotor approaches the object, thus serving to test the control algorithms. Classification results. Table 2 shows that using a window length of 0.4 seconds results in a better performance than 0.2 seconds in the validation set. This is explained by the fact that the algorithm has much more data from the past at each input for the recurrent layers to better discriminate the classes. Here we can see the result of applying a PI controller in the simulator, emulating the contact of the processes with an object, and a proximity reference of 0.7. The controller actuation leads the system to a relatively low error, presenting a noise signal inherent to the system. The gains used were Kp equals 0.1 and Ki equals 0.82. A PID controller was tested, but later discarded, since the derivative portion destabilizes the system due to the noise present in the signal. The PI controller performed better, with a small overthrust but faster actuation, compared to the proportional controller. Conclusion. The combination of CNN and LSTM achieved a remarkable accuracy, considering the application of only one SEMG sensor, as opposed to commonly used and far more expensive setups, with 10 or 12 sensors. Testing the control algorithms in the simulator beforehand prevents damage to the servo motors, saving time and minimizing costs. In the future, we could collect more data, automate the process of data labeling, and use some technique to mitigate the problem of unbalance the classes. Thank you for your attention.